Happy Friday, everyone, and welcome back to our Back to Basics series. Today, we have another special Ask Me Anything AMA session with the one and only Ron Hranac. That's right, we're back for round 2, giving you another chance to ask your questions about RF impairments, troubleshooting, best practices, and of course, what not to do in your cable plant. A shout out to the Great Valleys chapter for arranging the SCTE GLOM so you can get your credit, and the many other chapters who contribute to the success of the SCTE and its mission. Please do write in the chat which chapter you're with if you're joining from a chapter today. For those new to the channel, I'm Brady Volpe, founder of the Volpe firm and Chief Product Officer at OpenVault. And as always, I'm joined by the legendary Ron Hranac, a 50-year veteran of the cable industry who is a trusted resource on all cable matters. All right, Ron, let's dive into it. Welcome back. Are you ready for another round of questions?
Well, thanks, Brady, and happy Friday to you too, and happy Friday to those who have tuned in to today's live stream. This is fun. I'm looking forward to it. The last time we got together, we did an Ask Me Anything, and we had way more questions than we had time to answer, and I was surprised at how quickly the time went by, and I suspect the same thing's going to happen today. Just a point for those who are planning to ask questions, keep them RF related. I do not do DOCSIS questions. I'll defer to Brady and John Downey and others for those kinds of questions. But RF stuff, and I think last time we had somebody who might have been a cable TV subscriber complaining about their cable service, and we can't help you with that. You need to contact your cable company if you got issues there. But RF stuff, we're here to address your questions and have a good time today.
Indeed. And a shout out to Sean Lester in the chat room there. Sean, thank you, especially in your chapter, because you guys definitely helped us with putting together the integration with the SCTE for today's session. So definitely throw your questions in the chat room there, guys, and we'll start those. Ron, I want to start off because one of the things Ron, myself, a number of other people are always busy working at Cable Labs putting together new content for the industry. One of the things we've been working on most recently, Ron, is a discussion on noise. And I thought maybe we would enter into that. What are some common sources of noise that you see, Ron? Or is there just one source of noise that the technicians have to manage when they're trying to troubleshoot the upstream? I thought I'd throw that out to you.
Oh, that question is definitely one that falls into the category of it depends. And I don't mean that tongue in cheek. I'm very serious about that, because how do we define noise and what is it? Typically in a cable network, noise is usually meant to be thermal noise generated in, say, a 75 ohms impedance or in an amplifier. And that contributes to what we call carrier to noise ratio. It contributes to something called noise figure, which is a parameter that amplifier manufacturers put in their spec sheets and can measure. In fact, in the NOS working group that I chair, we're working on a draft technical monograph about noise figure. And that one hasn't been reviewed by the group yet, but will in the very near future. But it covers some of the stuff from way back. So that's the fundamental stuff. But there's an interesting type of noise that also appears in our cable networks. And this started to show up as the industry migrated from all analog TV channels in our networks to a mix of analog and digital signals, and then eventually to mostly or all digital signals. And that's basically distortion or noise-like distortion. It's known by a couple of different names: intermodulation noise, composite intermodulation noise, composite intermodulation distortion. And of course, in the old days of all analog networks, operators were very familiar with composite triple beat and composite second-order distortions, which were groups of discrete beats that appeared at certain places in the spectrum. But in all digital networks, those distortions don't go away. They just take on a different appearance, and they look like wideband noise. So what we get in our digital networks today is a combination of thermal noise and these noise-like distortions. There's no way to visually differentiate them on a spectrum analyzer, and where you'll typically see this is as you look on a spectrum analyzer at, say, the carrier to noise ratio, and you start at a low carrier to noise ratio and start cranking up the signal levels, you'll see the carrier to noise ratio get better, which is expected. But you'll eventually reach a point where the output levels of the active device, like an amplifier, generate a sufficient amplitude of this noise-like distortion where it starts showing up in the noise floor and mixing together with the thermal noise. And now, as you continue to increase the levels, the noise floor increases instead of decreases. So the so-called, what you thought was a carrier to noise ratio, starts getting worse. And here we're actually looking at what's called composite noise, which is the combination of thermal noise and noise-like distortion. So we have this carrier to composite noise ratio. And unfortunately, the only way you could differentiate thermal noise and these noise-like distortions would be to shut off all your active channels, and then you'll see the noise floor drop, and all that's left is the thermal noise. Now, underneath the umbrella of this composite intermodulation distortion or composite intermodulation noise, the noise-like distortions, we find things like common path distortion that tends to manifest in the return path. And in an all-digital network, it looks like an elevated noise floor. So those are the common types of noise in the network. Where things get really interesting with noise is when we get ingress interference from different sources. For example, power line gap noise, maybe interference from other noise sources in the over-the-air environment, bursty noise sources, impulsive noise sources, automobile ignition, static from lightning. The list goes on and on and on. And
many sources.
Well, yeah. And broadly speaking, we tend to call these things noise. I prefer to call the external stuff ingress interference and to differentiate it from thermal noise and composite intermodulation distortion. But yeah, this stuff can come from all over the place, inside our networks and outside our networks.
Right. So the thermal noise you're saying that's like generated by the RF amplifiers, maybe even an equipment in the head end, and these other noises, the over-air noises, gap noise, things like that's external to the RF equipment.
That's external to our networks, but in addition to amplifiers generating noise, a 75 ohm resistor at room temperature generates noise. That's thermal noise. I don't want to get into the math behind that, but it's basically caused by the thermal agitation at the atomic level. As the temperature increases, the atomic particles jiggle around, and that generates a measurable noise. And in a 75 ohm impedance, so 75 ohm resistor, if we measure the noise power in a 4 megahertz bandwidth, because that's the bandwidth for analog NTSC TV channels. It's just one I like to keep in mind. I mean, if you use a QAM channel, it's a different bandwidth, but use that bandwidth, the noise power bandwidth for an NTSC analog channel at room temperature, and I'll use the room temperature defined in that's used in the freeze equations, and that gets into noise figure. That's 290 Kelvin, so roughly 62-ish degrees Fahrenheit. That generates a noise power with an amplitude of minus 59.21 dBmV. If you want to use 68 degrees Fahrenheit for room temperature, which many do, then it's minus 69.16 dBmV. And you use that, you plug that into an amplifier, and then you measure the carrier to noise ratio at the output of the amp, and you find that wow, the carrier to noise ratio is worse than it is at the input, and that's because of the added noise from the amplifier, which is the noise figure.
Right. Okay, and so I know the question's coming in from Sean Lester, but I think there's actually a group of people in with Sean there. So the question is, Ron, years ago you wrote an article and referred to this as carrier to junk ratios. I humbly submit we use that moniker going forward.
I have used that, and I still use that. However, in things like the DOCSIS physical layer specifications and various SCTE standards and recommended practices and operational practices, in those types of documents, the powers that be tend to frown on things, terminology like carrier to junk. And although I'll sometimes use it with quotation marks around it to indicate that it's basically carrier to the stuff we don't like or the undesired stuff, which could include noise and ingress and any other kind of interference.
Right.
But yeah, I like carrier to junk. It's very encompassing and tends to describe a whole lot.
So, so you mentioned that RF amplifiers, resistors, all these make some amount of noise, and we kind of call that like the noise floor. And I would argue that we would say that noise is most of the time reasonable. We're going to have that noise in the plant, but what is probably more unreasonable and what we're more focused on is I'll use from Sean's group, the carrier to junk description. That becomes more problematic for for our subscribers, for our equipment. What are we looking for when we're trying to differentiate between our typical thermal noise floor, that the floor that is the noise that is always there in the background, and the more problematic noise that is coming in from maybe signals in the outside air, or probably, or even in from subscribers' homes? When does it become a problem? How do we see that as a problem? What should we do?
Oh gosh, there's more. There's more. It depends in the answer to this question, but it's a really good question, Brady. And you're absolutely right when you say that most of the time that thermal noise is something, it's there, and it's usually not a big deal, but it can be a big deal if the signal levels are too low. Then your carrier to noise ratio is out of whack, and you're going to have degraded performance in a variety of ways. One, if you think about analog TV channels where you have degraded carrier to noise ratio, strictly because of thermal noise, maybe because the signal levels are too low relative to the noise floor, then you see snowy or grainy pictures in analog TV channels. In digital video, you don't see that degradation. As with analog channels, as the carrier to noise ratio degrades, let's see on a dB for dB basis, as you reduce the RF signal level, or let's say increase the attenuation in an amplifier beyond where it should be, have too much attenuation, you get this gradual degradation in the picture quality. But
you get those snowy video, pictures in analog TV.
Snowy pictures. They slowly get snowier and snowier, or grainier and grainier, because of the decrease in the carrier level relative to the noise power. With digital signals, you don't see that gradual degradation. In fact, with digital signals, because of forward error correction and other things, you see crystal clear, sharp pictures. I mean, they're perfect. And then as the carrier to noise ratio continues to degrade, the received modulation error ratio continues to degrade, and then all of a sudden you reach the so-called cliff point, or the cliff threshold, where you start to see maybe some tiling in the digital picture,
and then they're gone.
And then another half dB degradation, and it's gone.
Yep.
It just goes away. With voice, let's say voice telephony, you might hear roboticized voice as the carrier to noise ratio degrades, because packet loss is increasing, and when the packet loss gets beyond the error correction capabilities of the transmission format being used, the digital voice goes away too. But you get that roboticized voice where it can't fix the broken bits anymore, and things go out of whack. But digital gives us that advantage of being able to provide very good quality service until you hit that crash point. So that's a plus, but it's a minus too, because just by looking at the picture quality or listening to the sound quality, you have no idea how good the performance is.
You don't know how close to that cliff
you are, right? You don't know how close to
the
cliff you are. You don't. And when you reach the cliff, it's gone. It's just plunk. It's gone.
Yeah, and so that's where noise can be really, really problematic. So we have this guy named John Downey who's asking a question. He says, please touch on near noise test and how the test equipment could have poor dynamic range and or signal level that is too low for a good reading. So I think noise near noise in the spectrum analyzer. I'm
going to say, John, first, welcome. I'm glad that you're able to make it today.
John.
And you bring up a good point about near noise correction. Spectrum analyzers, as an example, have horrible noise figure. When we look at, say, a trunk amplifier, the noise figure might be 8 or 10 dB, somewhere around there. That's pretty typical for the amplifiers in the outside plant. But a spectrum analyzer, is not unusual to see a noise figure of 25 dB to 30 dB. I mean, that's the nature of the beast. The problem is when you're using, say, a spectrum analyzer to measure carrier to noise ratio, and the same could be true of using a signal level meter, measuring a carrier and then measuring noise and then doing a bandwidth correction. If the carrier level is too low. That is, the carrier to noise ratio that you're seeing on the display is too low. It's not so much the dynamic range of the spectrum analyzer that's an issue, but the carrier level is close enough to the noise floor where when you measure the carrier level, you are measuring the carrier level plus noise, because the noise level relative to the carrier level is high enough that in the resolution bandwidth of the instrument and in the detector stage of the instrument, it's making a measurement of noise and carrier power.
They're adding together, and now it's giving us an erroneous measurement.
You get an erroneous measurement, and realistically, what you need to do is find out is the displayed noise floor on, say, a spectrum analyzer, the noise floor of the test equipment or the noise floor of the cable network. And the cheap and dirty way to figure it out, temporarily disconnect the cable that you're using from the spectrum analyzer and watch the noise floor that's being displayed. If the noise floor does not change, that's test equipment noise you're measuring. Yep. You're not measuring the system noise floor. If, however, you pull the input from the spectrum analyzer and the noise floor drops, that's a good thing. But if it doesn't drop at least 10 dB, you're measuring mostly instrument noise with some outside plant noise in there too. And when you're in that range where the carrier to noise ratio or the apparent carrier to noise ratio is low, you either need to use a spectrum analyzer that can take into account that and use firmware to do a near noise correction, or you can use look at an external chart. It's a graph that shows what the measured carrier to noise ratio is, and then how much correction you have to apply to that in terms of dB. So you have to apply it manually to your measurement to make sure you get an accurate measurement.
And John's suggesting perhaps the need for a preamplifier in front of the analyzer in some cases to get your signal high enough out of the thermal noise floor of the amplifier.
Well, yeah, and that can work sometimes. Sometimes it may not. It depends that's in play there too. But let's say you disconnect the input from the spectrum analyzer and the noise floor does not drop at all, or it doesn't drop at least 10 dB. My recommendation when you face that condition is first see if you can find a hotter test point and plug into that hotter test point, repeat that measurement or that little test. And if you get the noise floor dropping 10 dB or more, then you're good to go as far as measuring carrier to noise ratio. At that point, you're going to be off by, I forget the correction factor at 10 dB. It's around a half dB or so. You're going to be very close. But a preamplifier can be useful. You need to have a very low noise figure preamplifier, either external to the spectrum analyzer or perhaps one that's built in. But you need to take into account that is going to amplify noise and the signal. A low noise preamplifier is going to get us into the world of the freeze equation, where that first active stage is going to play a bigger role in what your overall noise factor is, and then the effective noise figure is. So you want to make sure just plugging in a preamp may or may not help. It
depends on the preamp too.
It depends on the preamp, but it depends on what the signal level is coming into that preamp. Even if it's low, that may not be enough. But you may also have to use a bandpass filter and other things with that, so you don't overload the spectrum analyzer. So John brings up a good point.
All right, and then from Sean Lester's group, it says, over the past few months, I've noticed an increase in LTE ingress in many customers across the country, particularly in bands 11 and 13. It goes on to say, have you seen this? Have the carriers recently increased their transmit power level to improve 5G performance? Other than tightening our ingress mitigation efforts, what other recourse do we have?
You don't have any other recourse. You need to tighten your plant. No, it's not a function of the LTE signals increasing in power. They have FCC limits like any other over-the-air licensed service that's transmitting signals into the over-the-air environment. What you may be seeing is an increase in the number of LTE towers as they move into the use of higher and higher frequencies to get higher data rates. What happens, of course, is they add more towers to improve the coverage while still being able to provide, let's say, 5G type services where they're providing higher data rates. So it's not so much that they're increasing their power as it is there may well be more of them. And so that means you just got to pay more attention to making sure the plant is tight. And the only way to do that is the tried and true methods of let's find out where leakage is getting out and then that usually indicates where ingress is getting in, and you got to fix those things. And sometimes you may go out and measure leakage and say, well, I don't see anything above 20 microvolts per meter. It's lower than that. But the reality is, with very few exceptions, when ingress gets into the plant, whether it's downstream or upstream, it usually gets in by multiple low-level points. Sometimes it'll get in by what I call a high-level point, but usually it's a bunch of low-level points. And that could be a loose housing-to-housing connector, a loose faceplate on a tap, a loose F connector on a drop. And then you start multiplying these in a neighborhood where you've got a variety of these low-level points. And this ingress gets in via multiple points. And then, of course, inside the plant, the magnitude of the ingress increases to where it's causing harmful interference to your signal. So you've got to go out and find all these low-level points and fix them. And sometimes that can be a real challenge.
Tighten those connectors and terminate. Jeremiah D says, can you shine a light on Annex B, 6 megahertz versus 8 megahertz Euro-DOCSIS and other 8 megahertz QAM standards? The landscape that drove these standards has changed. Are we doing the best we can staying with 6 megahertz?
6 megahertz or 8 megahertz, or in some countries, 7 megahertz.
Even 7 megahertz, right.
The bandwidth for the channels used in cable networks is largely a leftover, I don't want to call it artifact, but sort of like that. It's largely left over from the channel plans used by broadcasters, TV broadcasters in the over-the-air environment. So in Europe and many other locations around the world, the over-the-air analog TV channels used either 7 megahertz or 8 megahertz bandwidth, depending on the frequency range and depending on the country. 8 megahertz was very common throughout Europe. And in the Americas typically used 6 megahertz. There are a couple other places that use 6 megahertz, but that goes back to the development of NTSC analog TV channels. In fact, there's a standard that defines the 6 megahertz channel plan used in cable networks. And that standard is under the auspices of CTA, the Consumer Technology Association. So those of you that say you've got EIA channels on your network, you're about 20 years out of date. That designation was deprecated 2 decades ago and was replaced when the EIA no longer managed the channel standard, and it went over to the Consumer Electronics Association, the CEA. And the CEA changed its name to the CTA, and then the name of the standard changed. But it is CTA 542D, and then there's some other stuff that come after it, that something like R2023 or something. But that defines the 6 megahertz channel plan. So for digital signals in the Americas, we use the same 6 megahertz channel plan for both analog TV channels and digital signals, so single carrier QAM channels. In Europe, they use 8 megahertz. That's not going to change anywhere. They're going to continue in different parts of the world to use those band plans that they have always used. The technology supports it. The cable modems support it. The CMTSs support it. The standards are defined. DOCSIS and Euro-DOCSIS define those bandwidths based on the location. So Euro-DOCSIS covers stuff in Europe and elsewhere using 8 megahertz bandwidths, and in North and South America and some other places, 6 megahertz. Now, is that the most efficient use of the spectrum? The answer is no. Spectral efficiency, or bits per second per hertz, isn't bad. With a digital signal, as you increase the modulation order, you increase the number of bits per second per hertz. That's good. You can get pretty high data rates doing that, but you're still not getting the maximum spectral efficiency. Where the better spectral efficiency comes into play is with DOCSIS 3.1 and later, using OFDM in, say, the downstream and the upstream, but in particular in the downstream. With OFDM, you're not limited to 6 megahertz or 8 megahertz channel plans.
Right.
And the bandwidth of a DOCSIS 3.1 OFDM signal can vary from a minimum of 24 megahertz to a maximum of 192 megahertz. And you don't have those gaps in between, every 6 megahertz or every 8 megahertz. So the spectral efficiency is much better, which supports higher data rates. And then you throw in the much more powerful forward error correction technology.
I was going to say LDPC, which is the better error correction over Reed-Solomon.
That gives you about a 3 dB bump over the Reed-Solomon error correction used with legacy single carrier QAM channels. So we're never going to get away from 6 and 8 megahertz spacing. That's always going to be there. But as the industry migrates away from what I'll call legacy DOCSIS and digital video transport using those channel bandwidths and moves more to OFDM with DOCSIS 3.1 and 4.0, then you'll see the improvements in spectral efficiency and the much higher data rates supported by that.
Yep. John says we're moving to OFDM anyway, so no 6 or 8 megahertz either way. Spacing will still be there, but we've also removed MPEG-2 encapsulation that is in DOCSIS 1.0 to 3.0. So improving.
Well, he's got one thing wrong in there. He says so no 6 or 8 either way. With the 6, yes, that's still there with OFDM, but what it applies to is the OFDM channel power. Correct. Which is defined in DOCSIS as the power per CTA channel. That is exactly the way it's written. It is the power per 6 megahertz. So that doesn't go away. But of course, then we get into the 6 versus 8. The Europeans said, well, we don't like the power per CTA channel because we don't use CTA channels. So we want to convert the DOCSIS channel power or the OFDM channel power to power per 8 megahertz. So they've got to do a correction to that. But if you look at modern field meters, they can display the power per 6 megahertz. I know on the Viavi One Expert, it has this graph of the OFDM channel. It shows these little blue horizontal lines that represent graphically the power per 6 megahertz or the power per CTA channel. But that's actually spelled out in the DOCSIS physical layer spec. So that doesn't completely go away. I know where John's coming from, and I got to give him crap.
Yeah, he says you got him on that one. So.
I know. John and we've known each other for way too long.
Yeah. Caleb says, I'm seeing the LTE getting in at the head ends, well-maintained and well-terminated head ends.
Oh, yes. And that's getting in. And this is not new. This was discovered several years ago, particularly at head ends and hub sites that were co-located with, say, a tower next to the head end building where maybe the cable company was leasing space on the tower to one of the phone companies, and they had cellular transmission equipment there, and they were finding that they were getting interference from LTE signals directly in some of the optical transport equipment. They were getting it directly in their test equipment, even with nothing connected to the input of those devices. And they put a 75 ohm terminator on the F connector on the input to their test equipment or their other instruments, and the interference was still there. The interference in that case has to do with the shielding, or I won't say lack thereof because there is some shielding, but the shielding quality of those devices. And I remember the first time I heard of this in a major operator's head end site where they got this kind of interference, they said that they were estimating the field strength in the head end, and the field strength just sounded ludicrous. So I did a quick back of napkin calculation with one of the engineers from that company, and I said, no, you should be more like this, because you have to take into account the main beam of the antenna is going out this way, and you've got side lobes, and they're going to be, and I think I picked the number, 10 dB down, and then you got some attenuation through the cinder block wall and stuff. And I calculated the field strength in the head end, and that same operator later brought in I think an engineer from Rohde and Schwartz who had a very expensive piece of test equipment that could accurately measure test equipment or measure field strength, and their measurement was almost dead on with what I had calculated.
Of course it was.
Which is still high. It was still high, but it wasn't nearly as bad as somebody had tried to estimate or measure. And but the gist of it was
Faraday cage for the head end.
It was optical. It was optical. It was some optical transport equipment, downstream lasers, that was affected by this. And of course, at the time, I worked for a vendor that made that kind of stuff. And I said, is that our product? And they said, no, it's somebody else's. And the manufacturer of that equipment had to do some tweaking to the design of the shielding on the enclosures, basically the modules and everything else. So they had to put new finger stock in and a bunch of other stuff to improve the shielding. The company I worked for had done testing. They tended to be so conservative on stuff. Their stuff was rated for 10 volts per meter field strength, which is just an insane field strength. But that's kind of beside the point. No, the issue there is if you see that getting into equipment in the head end or your test equipment, the culprit is not the LTE signal itself. It is the shielding integrity of the affected equipment.
Yep. And that's
You
an
got to work with your
expensive
manufacturer.
fix to go back and do.
Well, you go to the big, let's say with spectrum analyzers, you go to the big names like, well, HP now, Agilent, and then what are they today? Rodian Schwartz and others. They design Keysight is what Agilent became. They design their stuff to be usable in high field strength environments, typically to 10 volts per meter or greater, which is very, very high, very, very high level of shielding and robustness in ambient field strength.
All right, so Sean was going back to the 6 megahertz, 8 megahertz OFDM discussion. He's saying, as we're well aware, he firmly believes bits per second per hertz is one of the best measurements we have on how well a DOCSIS network is performing. He also says he will call it EIA to my grave. So,
EIO.
Yeah, and I see a lot of even current documentation I see out there with EIA channels still being used. I think it's going to take us a long time to change.
Old habits are hard to break. I'll grant Sean that, but it is CTA. The EIA designation it literally went away and was deprecated over 20 years ago. So that terminology is no longer accurate. It is the channel plan falls under the CTA standard and has for a long time.
All right, and Local Trees, good to see you in there. Thanks for joining again, folks. Get your questions in there. I'll ask Ron a couple more here. Ron, one I want to ask you on is group delay, because that's a very common question I get from people. What is group delay? What causes it, and how does it? Does it even cause an impact? Is this something we should worry about in our networks?
Well, last question first. The answer is yes, it's something you should worry about, but in some cases it's something you may not be able to do anything about. Where does it occur? Group delay distortion, and I'll give a kind of a high-level definition of it here in a moment, tends to be more prevalent or occur more often at the edges or near the edges of a bandpass in a spectrum. So think of, let's say, the upstream spectrum as the equivalent of a bandpass filter. So we pass signals from 5 megahertz to, say, 42 megahertz or whatever, but I'll use 42 megahertz as an example. Down at 5 megahertz, we have that frequency response roll-off, which attenuates signals below 5 megahertz. Doesn't get rid of them completely, but it attenuates signals down there. And that's a function of a couple things. One is the frequency response of the amplifier circuitry, and the other is the so-called lightning filters that are used in amplifiers to help minimize, the effects of surges and noise from lightning. That's stuff that's built in. So there we've got the equivalent of a bandpass filter on one end. At the other end, we run into the diplex filter roll-off. So the diplex filter, the part that passes the return path, is a low-pass filter. So there's some roll-off at the upper end. So now we have this bandpass filter, and near those band edges, the same's true in the downstream, we have these roll-off areas where the group delay tends to be worse. All right, so all that said, what is group delay? So visualize this. So this is something that Tom Williams, who's now retired, he used to be with Cable Labs, described it this way. And this was such a good description. I created an animation in a PowerPoint slide deck that I did on group delay distortion. And he said, imagine a track where you've got a bunch of athletes running down the track to the finish line, from the start line to the finish line. And they're more or less, let's say they've got evenly matched athletic abilities. They're all more or less going to reach the finish line at the same time. But if you have more runners than you have track, where do those runners on the edges go? Well, they got to run through the ditches next to the track, through the weeds and the mud and stuff. So they get slowed down relative to the runners on the asphalt. And the runners on the asphalt arrive at the finish line sooner than the
guys getting bogged down and all that.
They're getting bogged
nastiness.
Down. They're running through the ditches. So the analogy is that the ditches are like the roll-off areas in the spectrum. And the group delay distortion means that at frequencies where the roll-off occurs, because of some factors I'm not going to get into because it's going to get way too deep, the time delay through that part of the spectrum is greater than the time delay through the flat part of the spectrum. So visualize that roughly 5 to 42 megahertz return path And again, this would apply to a
That's your nice running track where everyone can run.
We've got a nice running
right.
track, and all the frequencies arrive at the destination, whether it's going from cable modem to head end or whatever.
Yep.
They all arrive more or less at the same time. But the frequencies in that roll-off area, because of that nonlinear amplitude versus phase relationship that's going on there, those frequencies take a little bit longer, typically measured in tens of nanoseconds or hundreds of nanoseconds. They arrive later. And if you've got group delay distortion within a digital channel, some parts of that digital channel arrive later than other parts of the digital channel. And the result is you get this, we'll call it a kind of a time smearing, but you'll get a degradation in the receive modulation error ratio. And the group delay distortion that exists in diplex filters and amplifiers and stuff, you can't do anything about that. That's there. You can't get rid of that. I mean, you can reduce the cascade depth and you can improve the group delay distortion performance, but you can't get rid of it. That's a matter of physics, and that's the way the edges of those filters work. That's where something called adaptive equalization or adaptive pre-equalization comes into play. It can compensate for that. It doesn't get rid of that distortion. It compensates for it. So an adaptive equalizer, let's say in the upstream or pre-equalizer, the effect there would be, if we go back to the athletes on the track are slowed down by the group or by the adaptive equalizer or pre-equalizer to let the runners in the ditch catch up so that when they all arrive at the destination, they all get there at the same time. So that's kind of what's going on with adaptive pre-equalization. Think of it as sort of slowing down the runners in the middle of the track and letting the other ones catch up so that all the frequencies arrive at more or less the same time.
That's a great analogy for group delay. I got to say, Ron, I'm going to have to use that in the future when trying to explain
I've got I'll try to remember, send me an email or something and I'll send you the PowerPoint because I did the animation that shows that. And I think it really helps to describe what's going on.
So, I mean, fundamentally, we know group delay, if it's not compensated for by the pre-equalizer, if it's so high, it can cause issues for the modems, uncorrectable code word errors, or eventually it could even cause the modem to lose that channel that is being impacted by group delay. So we know it's problematic.
When group delay distortion occurs, it trashes the modulation error ratio, or the MER. RX MER is really what it is. And if the RX MER gets low enough, you can start to suffer bit errors and packet loss, and pretty soon the FEC, the forward error correction, can't fix it, and now you've got packet loss.
Yep, absolutely. All right, so Local Tree says, happy to be here. Nicholas P. says, group delay is definitely a hard one to understand. Great explanation. And I agree, it is not something that's easy to explain, but we do see issues with it, and something that... I first really started looking at group delay when I got into PNM, proactive network maintenance, because it would be something that would show up there. But because we're using pre-equalization, we could see really high group delay values. And if you're familiar, there's a DOCSIS specification that says your group delay must be less than 200 nanoseconds per megahertz. But it's very common with pre-equalization to see group delay values at like 1,000 nanoseconds per megahertz, way beyond the spec. But the subscriber's not complaining. Their modem is behaving quite well because of pre-equalization compensating for that.
Now, here's an interesting thing that folks that have been in the cable industry a long time, going back into the days of analog TV channels, may not be aware of it, but do have experience with group delay. Now, not only did the amplifier manufacturers specify group delay, typically in stated for channel 2 and channel 3, but in the forward path. But in-channel group delay manifests as something called chrominance to luminance delay distortion. And inside of an analog TV channel, I'll go to an NTSC channel, visualize you've got visual carrier here, and you've got the color subcarrier here, and then the oral subcarrier over here. And the luminance information is carried in the visual carrier, well, not carried in the carrier itself, but in the luminance sidebands that are spaced 15.734 kilohertz apart. A little bit on the lower sideband, that vestigial sideband, and then going up the other direction. Then the chrominance information is carried in the chrominance sidebands as phase and amplitude information, kind of like QAM, phase and amplitude, but those sidebands are spaced in between the luminance sidebands, and they're every 15.734 kilohertz. So now if you have group delay inside of the 6 megahertz channel, the color information may arrive at the TV set slightly later in time than the luminance information, and we get what was called the funny paper effect, where you see the outline of the image and you see this color smearing off to the right of the image.
It's called ghosting, right?
Well, no, it resembles ghosting, but with ghosting, the entire channel is offset in time by the delay that second path took.
Okay.
Or the signal path took. In this case, within the channel, because of the group delay distortion there, the color information, which is 3.5 megahertz roughly above the visual carrier, took a little bit longer to get to the TV set than the luminance information did. So the color doesn't register exactly with the outline of the image, and you get this color smearing or an offset in the color, kind of like looking at the funny papers in the Sunday Funnies for when people used to get those. You might see that during the printing process, the color was offset from the outline of the cartoon. And that's why it was called the funny paper effect. So people saw that and may not have known what it was, but that was a type of group delay distortion. Where it really showed up was in character generator channels, which has real fast rise time and fall time on those characters. And you'll see that smearing off to the right of the lettering. That's caused by that group delay distortion in the channel.
Definitely saw it many years ago. So Jeremiah D says, can group delay affect SNR? Does modem traffic arrive at the wrong time and step on other modems in severe cases?
Not so much in the way that you're describing. I mean, that's a really good question. Some people call RxMER SNR. They'll say, what's my downstream SNR or upstream SNR? When they really mean MER, modulation error ratio. Group delay distortion, if we think of SNR as basically being carrier to noise ratio in the frequency domain, group delay distortion doesn't affect that. So the answer there is no. It does affect MER. And if you'd like to call MER SNR, then yeah, it would affect that. But it affects the RX MER. And what it's doing is it's smearing the data in time because of that in-channel distortion. It's not so much that you're going to get modems stepping on one another, because at that point you're getting into modems transmitting at different times. So no, it's not going to cause that. It's going to cause a degradation in the MER or RX MER specifically of that signal, which can, if it's severe enough, cause packet loss. But hopefully the adaptive equalization will compensate for that.
All right. And Nicholas follows up with, how bad is group delay in the downstream? I was in a discussion with a colleague recently, and we didn't quite know how it would occur or be mitigated.
Well, it's the same thing I described a little earlier. In the downstream, let's visualize now the downstream starting at channel 2, so 54 megahertz. The amplifier manufacturers would publish a group delay specification for the diplex filter, and that's where it's affected by, is the diplex filter largely that separates the downstream from the upstream. So you've got that roll-off just below channel 2. So the group delay distortion tends to be worse there. So manufacturers would specify group delay in channel 2, maybe also channel 3. You can't do anything with amplifier adjustment or anything else to mitigate that. You can't get rid of it. That's inherent to the design of the filters that are used in the amplifiers. What you can do is, if you're what you want to make sure you do, if you're transmitting digital signals near the lower band edges, make sure that you're using adaptive equalization in your data receivers. So your cable modems should have it on all the time, and that should compensate for the group delay distortion where it can occur. And that could be at the lower band edge. If you have a suck out in the frequency response where you have that rapid amplitude versus frequency change, you can have group delay distortion there too. So any place where you have the, let's say, amplitude ripple or the suck out, or you're at the band edge, you can have group delay distortion. For things like suck outs and amplitude ripple, you can fix the problems that cause those. But for the group delay distortion that's inherent at the band edge, you can't do anything about that. But if you have digital signals there, the adaptive equalization should be able to compensate for it. And you could reduce the cascade depth, which means you'll reduce the cumulative group delay distortion and you'll be in good shape. But that may not be practical. You may not be able to go out and reduce the cascade depth.
All right, John says, comic book effect. Channel 2, since it's the first channel, the hack was to pre-distort 170 nanoseconds the opposite way, so you could double your amp cascades.
You could, but you want to be careful about doing that beyond how it's done in NTSC video transmitters, like head-end modulators. They have a pre-distortion in there to compensate for that, and I think it is a 100 nanosecond delay. It's done in broadcast transmitters. It's done in modulators. Well, I'll say some modulators, because when I ran the corporate evaluation lab at Jones Intercable back in the 80s, I used a precision Tektronix demodulator and a VM700 automated video test set, so I could measure all of that. And I was surprised to find that some head-end modulators did not use that pre-distortion that's used in some of the better quality modulators and in broadcast transmitters. And the idea there is it's designed to offset. There was some group delay caused by what was it? The oral carrier notch, I think, in the video circuitry. So you're not getting video information. So that you're not getting that interference, I think, is where that came from. But yes, there was a pre-distortion that was used in broadcast transmitters and some of the higher end modulators. And where a modulator that was low cost did not include that pre-distortion, you could see the comic book effect and say, where the heck did that come from?
Very good. John asked a follow-up question, which I think is actually a good question, John. Can severe standing waves cause group delay or maybe even a suck out, Ron?
It's not a suck out, but it's, well, not in the strictest definition. But I answered that previously, but maybe it didn't come across. But the answer is yes. Where you have, let's say, standing waves in the transmission line, the coaxial cable, that manifests as amplitude ripple in the frequency domain. Yep. And where you have these rapid variations in amplitude versus frequency, you can have group delay distortion form there. So what you get is group delay ripple. And the adaptive equalizer should be able to take care of that in most cases, unless it's really, really severe. But then you've got to go out and find out and fix the impedance mismatches that's causing the standing waves and the subsequent amplitude ripple. But yes, severe amplitude ripple can cause group delay distortion. It's group delay ripple.
Yep. Yeah, no, I think that's important to understand. Jeremiah D says, I'd hate to do the biannual proofs on that cascade, LOL. And I think it'd be good, what do we mean by biannual and what are proofs? Or why do we do them twice a year? Biannual is twice a year. What is a proof, Ron?
Well, the concept of what's called a proof or a proof of performance has been required in Part 76 of the FCC rules for pretty much as long as I've been in the cable industry. That goes back to the early 70s. Back then and into the 80s, I don't remember when the FCC rules changed it to twice a year, but it used to be once a year. And I would go out to cable systems in the region where I was the regional engineer for Jones and do or help with the proof of performance tests. And the FCC rules in Part 76 spelled out a number of technical performance parameters in 76605, with measurement techniques described, I think, in 76609, if I remember right, for the analog NTSC TV channels carried in the system. They had to do all kinds of measurements as part of that proof of performance testing. The FCC bumped that up to twice a year, with the idea being that you get an indication of what the cable network performance looks like in, let's say, the summer when you do one of the proofs, and the other one in the wintertime when you do the second proof. So the idea was to make sure that the analog TV channels, and I think the intent of the rules was to make sure that the cable network wasn't degrading the performance of the analog TV channels beyond a certain amount. And those proof of performance tests were done and were required to be done to ensure that. And you had to record all kinds of things like the make and model, last calibration date, serial numbers, and so on of the test equipment being used, and also the name of the person or persons doing the proof, along with the qualifications of the person or persons. And then it had to be put in writing and logged and put in a file cabinet. So if the FCC came to visit, your cable system, they might request a copy of your latest proof of performance test and measure your latest signal leakage logs, and you had to pull that stuff out of the file and be prepared to hand it over for review.
Yep. And so that does just apply to our our operators in the United States, and I know that's something, Ron, you strongly encourage that people continue to do, whether they're carrying analog channels or not, for that. So, Nicholas P. taking us back to group delay. How bad is group delay when going into the roll-off of an 862 megahertz amp? We're thinking of deploying an OFDM channel around 862 megahertz to 1 gigahertz. Should I be worried? This is only for a brief time as amplifiers are going to be changed.
The nice thing is, at least in the downstream, the roll-off above the upper frequency limit of the downstream spectrum tends to be more gradual than you would see it at the lower end. So the group delay distortion, and there will be some, but it's not going to be as severe as it is at the lower frequencies. Where you can see some issues might be in the feeder part of the plant, where you've got a lot of, and I'll just pick on a 750 megahertz plant. Let's say you've got a 750 megahertz plant. You've got the gradual roll-off in the amplifiers at 750 megahertz. You've got the gradual roll-off through the passives, the taps, and splitters, directional couplers, and stuff. And that might, depending on the layout of the plant, might get a little nasty looking at the upper end. But surprisingly, I've seen cable operators carry DOCSIS OFDM signals in the roll-off region in a 750 plant. In fact, my neighborhood used to be served by a 750 plant for the longest time, and there was an OFDM signal when the local cable operator first rolled out DOCSIS 3.1 a few years back that operated in the roll-off, and it worked fine. The adaptive equalization took care of that roll-off and group delay. Now, as you're migrating to a greater bandwidth, I don't know that the group delay is going to be so much of an issue as just managing signal levels and other things as you make the swap from, let's say, the 862 amps to 1 gigahertz amps.
Yeah, and I definitely agree with you that roll-off is is not so sharp as we would see with filters and things like that. It tends
to be a lot gentler.
Yeah. So, Ron, I have one crystal ball question for you as we're wrapping up the episode here. With the industry moving toward DOCSIS 4.0 and fiber deep architectures, lots of talk of fiber. Do you think HFC will still be a dominant technology 3 years, 5 years, maybe even 10 years from now?
My favorite answer to so many questions is it depends. I think HFC is going to be here for the foreseeable future. It'll certainly be here in 3 years. It'll be here in 5 years, probably 10 years. What you'll find is that as more operators roll out fiber to the home, and I think the European cable operators tend to be more aggressive about rolling out fiber to the home than we are in the Americas. But looking at even the major cable operators here in the U.S., I think all of them have at least some percentage of their homes passed served by fiber to the home. For the most part, near as I can tell, it's in single-digit percentages. But over time, that's going to increase, and it'll be over time. And the reason is first of all, it still costs a lot of money to rip out an existing HFC network and replace it completely with fiber to the home. If you're doing a greenfield build that is brand new from the get-go, there is no HFC there, fiber to the home makes more sense. But in where you've got existing HFC, we can still do upgrades to the HFC part of the network and take advantage of the incredible capacity of coaxial cable. A lot of people think, well, where does coax run out of gas? I don't know, maybe a couple of gigahertz. Yeah. DOCSIS 4.0 supports downstream operation to 1.8 gigahertz or higher. How much higher can you go? That's another, it depends, but the connectors, call it the hardline connectors, the hardline coax, are all, if you look on the spec sheets for the manufacturers, are for the most part specified out to 3 gigahertz. So that's going to give us a lot more expansion room for the foreseeable future. But the other thing is, well, what about just the capacity of coax? How high can we go? And how high can we go in terms of the capacity? I'll start with the bandwidth for the upper frequency limit, depends on the physical dimensions of the cable. And you get into something called the transverse electromagnetic mode of the signals passing through it. And what that means is that larger diameter cables have we'll call it a TEM mode cutoff. Let's say 750 cable cuts off at about, 750-ish about 7.5 gigahertz. Half-inch hardline cable is good to about 11.5 gigahertz. Series 6 drop cable is good to, I think it's, the math I did was about 26 gigahertz. Now, in the smaller diameter cables, while they can handle higher frequencies, at least from the perspective of the capacity, the attenuation is worse with lower or smaller diameter cables. I wrote an article in Broadband Library a few issues back about talking about the capacity of coaxial cable, and I went through the math and showed the examples of what you could get, and I figured that conservatively, you could easily get to 6 gigahertz for an upper frequency limit in a cable network, and I made some assumptions and said, let's just divide the forward and return up in half at 3 gigahertz is the cutoff for the return, and 6 gigahertz for the downstream, with it starting at 3. And I said, assume no diplex filter roll-off or crossover losses. And there are some amplifiers that can do that without diplex filters. And I'm trying to remember the data rate I came up with it. And I don't remember if I used 4K QAM or if I went higher, but the data rates were something like 25 gigabits per second symmetrical.
It's amazing.
With coax. So the capacity's there. At that point, we may say, all right, we don't want to keep upgrading the coax plant. At that point, we'll just go to fiber. But we don't have to rip it all out. That fiber's got the coax has got a long life ahead of it.
It's really amazing. I mean, I always tell the story 30 plus years ago when I was starting out my career in cable. I was telling my boss that I don't think cable has a future. I need to go find a new job. And he says, Brady, give it a couple years. There's probably some future in cable. Here we are more than 30 years later saying, yeah, there's still more future in cable, and I definitely think there is. So Nicholas says, I did not do a cascade test yet, but with 2 amps, I was getting a tilt of minus 17 dB. This was impressive as it did not work perfectly.
It did work perfectly.
It did work perfectly. Yeah, I mean, that's the amazing thing that we're seeing with OFDM deployments. Sean Lester says the engineer's mantra. It depends.
Yes, it depends. Yeah. I mean, there's some black and white stuff in there where, it's got to be this answer or that answer, but there's a lot of it.
There's a lot of gray in between. Yeah. Dominic, welcome. He says, what frequency should you put your regular digital cable linear TV above 860 below? And where should you put the doctor's internet, or the DOCSIS internet, I believe? Yeah, he says he's at the doctor's office doing voice chat, so he's having his... So wait, put your video... I think we normally say keep your video as low as you can and put your DOCSIS as high as you can.
You can do that, but you don't have to. The nice thing is the DOCSIS spec supports downstream operation with DOCSIS OFDM channels all the way down to 108 megahertz. Yep. So you can put it there. In fact, I know of at least one cable operator that did just that, put their DOCSIS OFDM signal on the low end of the spectrum and then their legacy stuff at the high end of the spectrum, and they cranked up the OFDM channel 3 dB relative to what legacy digital video would have been. I remember doing some between midnight and 6 a.m. field tests with a cable operator in one of their markets, and then I said, you guys don't have to do this in the nighttime. You can do it in the daytime. We did one other field test in another market in the daytime, and they had done a lot of lab testing ahead of time on the bench to make sure the equipment could support this configuration, and it worked fine by putting the DOCSIS stuff down low and the legacy digital video up high. Put it anywhere you want. But as Brady said, most people put the SC QAM stuff down at lower frequencies and the DOCSIS stuff at higher frequencies, but you don't have to.
Yeah. So hope things go well at your doctor's appointment there, Dominic. John says, Ron, that's exactly what I tell customers. If you have HFC already, it's almost always better to continue using it.
Usually cheaper.
Usually cheaper. And Ron and John, you like this one. Nicholas P. says, for us as German DOCSIS providers with 100K subs, we are migrating from a UBR 10K with MC 20 by 20 cards, using HFC to harmonic DAA with DOCSIS 3.1. We are also heavily focusing on fiber to the home with XGS PON. Those UBR 10Ks are still out there running.
They're still out there. That's
like the Energizer Bunny.
Or something. But yeah, and that's fine. Keep using the technology. Get your money's worth out of that. And doing what a lot of operators are doing. They're using their legacy big iron chassis, and they still use it, and they're migrating to some type of or form of fiber to the home. usually a PON-based architecture, and that works fine.
Yep.
Ultimately, I think that's the end goal for the industry, is to get the fiber to the home. It's just
Absolutely.
I remember people saying in years past, "Well, it's another 5 years, and it'll be more wide." There's always another 5 years, and we're still not there yet. But
anyway, Grandpa Sandwich says, "Remember when Clinton Gore said we'd all have fiber to the home by what was it? Year 2K? Y2K?"
Yeah, here we are, a quarter of a century later.
Good memory. Sean Lester says he's been recommending OFDM channels to be moved to the lower frequencies and all video in the higher frequencies. So
works fine.
Yeah,
you can do it if you want.
You just said that. So
yes.
Great chat, everyone. Great conversations and great information, Ron. Thank you so much. That was absolutely great knowledge that you shared with everyone, and we really, really appreciate your insights. They're always invaluable and truly appreciated. Eshraga just dropped in. Our OFDM is below 100 to 500 megahertz with a few SC qualms at 350 until they swap out their old modems. So, again, thank you, everyone who joined us live. Your questions keep the discussions going. Without you, it'd be pretty quiet on here, definitely in an AMA. If you didn't get your questions in, do drop them in the comments below. We'll try to cover them in a future episode or answer them directly. If you enjoyed today's live stream, please do hit that like button and subscribe. Turn on notifications so you don't miss an episode. And don't forget, you can catch up on past episodes of our Back to Basics series on YouTube, Spotify, Apple, and Google Podcast. Thanks again, Ron. We still have questions coming in, but we'll catch up on those later. So thanks, and thank you, Mia, for moderating everything. Take care, everyone.
And my pleasure. Thanks, all.
Thanks. So long.